All right, welcome to Chapter 10. Chapter 10 is going to be on statistics and probability. So those of you who are going to AP Stats next year, this is your chapter. This is your time to shine. First of all, we're not in Chapter 9 anymore, so put those notes away. You might have to go on Google Classroom and print them out. Also, along with that, I attached some dice paper. I have this dice paper handy. There's 4 of them that you don't need all 4. You just need one corner of it. We're going to talk about probability of rolling different things on dice, and it's really handy to have all the options right in front of you so you don't have to actually roll dice or write it out or anything. You can just look it up. So when it comes to probability, there's a bunch of vocabulary that we need to know. Some of it's pretty basic, but we're going to write it down anyways. So here we go. First thing we're going to talk about are different experiments. Experiment is an activity, just an activity with multiple possible outcomes. So it's pretty vague, meaning basically anything that you do can be an experiment. You can roll dice, there's different things that can happen. You can draw a card, that's an experiment. I guess you could boil water and see how long it takes. So all of those things are going to be experiments. An outcome is, this is each thing that could happen. When you do it, there's different things that could happen. So if we're talking about rolling 2 dice, here are your outcomes right here. All of this, this is a list of each thing that could happen. If we're talking about adding them up, here are your outcomes right here. These are the different sums, 2 through 12. So what I would like you to do, one sec, is you can do what I've done. We'll get through this vocab, but I took 2 dice and rolled them, added up the 2 dice, and then did a little tally for how many times I got each sum. So rolled them up. If they add up to 7, put a little tick mark here. And so find 2 dice, roll them 36 times, and tally how many times you get each sum. And notice I put it in RF and not under PX. We'll talk about what those 2 things mean in just a sec. All right, once you have that, we're going to go back to sample space. A sample space, first of all, is a list, and that can be annoying. Is when it asks for a sample space, I'm not saying, hey, there's 10 different things that could happen. No, the sample space is literally you listing out every single thing that can happen, so it can be tedious. And you have to list all outcomes. So if we're talking about rolling 2 dice, this right here is your sample space. There's 6 columns and 6 rows, so there's 36 different things. The sample space is not 36. The sample space is a list of each one of those 36 things that could happen. All these outcomes here, there's going to be one specific event that you're going to be looking for. So this is the outcome we are testing for. So I want to say, what's the probability? You get a 7, you roll a sum of 7. Well, the event there is rolling a sum that's 7, the outcome we are testing for. Probability, that just means likelihood. How likely is it that something is going to happen? If we're going to do this, the shorthand notation, we're going to write P for probability, and then in behind it, we're going to put E, the probability of an event. So it'll list an event. If I want to know the probability, and I just ask you for P of E, like that, what's the probability that that event happened? Probability distribution is a list of all outcomes, and each one is going to be paired with its probability, and we'll do that at a later time, with its probability. So you're going to list something that could happen in the experiment, and then you're going to write alongside it, put the probability that it would happen. So pause one sec, see if you can identify each of these in the next situation. Situation is this: I have 2 dice, and I want to see how likely it is that I roll doubles. List each of the following. All right, the experiment is just rolling dice. The sample space, if I wanted to be mean about it, I would say, all right, you have to list 1, 1, rolling a 1 and a 1, and then 1, 2, we get sick of that real quick. And so instead of making you list them all out, you can just, hold up this piece of paper and say, there's my sample space. The event is rolling doubles. That's the specific event that we're trying to find. And then the probability that happens. The way that you calculate probability, excuse me, is in the denominator, you put your total number of outcomes. All the different, you make a list of all the things that could happen, and you figure out how many of them there are. So for rolling 2 dice, your total number of outcomes, I already said it on here, is if there's 6 columns and 6 rows, that's 6 by 6. There's 36 different things that could happen. The numerator is going to be the number of ways to get the event. The number of ways to get the event. So on bottom, the total number of things that could happen, there's 36 different ones. The event is rolling doubles. So what I have to do is go on here and figure out how many different ways are there I can roll doubles. Well, a 1 and a 1, there's 1, 2, 3, 4, 5, and 6. So there's a 6 out of 36 chance. If I simplify that fraction, that's 1/6. Or we could also write probability as a percent. You can go 1, if I turn this on, 1 divided by 6, and have a 0.16 repeating. 0.16 repeating. Or we could also call it a 16.6 repeating percent chance. All different ways that are acceptable to write probability. All right. What we just did, guys, is we just found, when we did the experiment, this is what's called a relative frequency. If I want to put a little line down here, relative frequency is when you actually do the experiment. Actually do the experiment. So this is what actually happens. Okay? When you do an experiment, it might match probability or theory exactly, but it might not. So results will vary. Meaning you might do the experiment and get one result, and I'll do the experiment and get a different result, and that's okay. We can have different relative frequencies. That's why I put RF here. If you actually did this and tallied it, that's a relative frequency. You did the experiment and figured out, what's the relative frequency that you would get a 2? Well, for me, it's 1 out of 36. For a 3, it would be 5 out of 36. Yeah, different than, it might not match theory. It might not match theory. In theory, if I'm looking at this, there's one way to roll a 2, so a 1/36 chance. What should happen, if I'm talking about getting a sum of a 3, well, there's 2 ways to do that. I should have gotten 2 tallies right there in theory, but I didn't. My experiment didn't match reality. Probability, on the other hand, is based on theory. This is what should happen. Not that it necessarily will, but this is what should happen according to math and how many outcomes there are. This is the same for everyone. Meaning, if you do an experiment, and I do an experiment, the probability you get a sum of 2 for you and I is the same. The relative frequency may be different based on the way our experiment just happened to turn out. So let's see. If we're talking about probability here, the probability you get a 2, well, 2, there's only one way to do it, so I should have a 1 out of 36 chance. There's a 1/36 probability of doing that. Same if you want to get a sum of 12, you'll notice some symmetry that happens here. There's one way down here to get a 12. How about a 3? You can notice the sums go in diagonals. So here's a sum of 3 and a sum of 3. So there's a 2/36. So I could simplify my fractions for now. I'm just going to leave them like that. Sums of 11, also a 2/36. And it doesn't take long to figure out the pattern that they're just climbing by 136 each time. So the sum of 4 goes right in here. There's 3 different ways. So we have 336, which you could write 112. Same over here. And now we can just kind of take the shortcut. 4, 4, 5, 5, and 6. All of them over 36. So the most probable sum that you could possibly come up with is right in the middle, would be a 7. That's the most probable thing. All right, we're going to try 2 more examples, maybe 3, and we'll call it a day. So see if you can do this. Consider flipping 2 coins. What's the sample space? Remember, the sample space is a list. So a list, the first thing that could happen is heads, followed by another heads. Then heads, followed by a tails. Then you could do tails, followed by another tails, and tails followed by heads. So there's 4 things in the sample space. Do all events have the same probability? Well, if we're not considering order, then maybe not. So what would be, we're going to write this as this. What's the probability of getting heads followed by heads? What's the probability of getting 2 heads? Well, it can happen 1 time out of 4, so we're going to call that 1/4. Same thing for the probability of tails, tails. There's 1 of those out of 4, so 1/4. And then over here we're going to call it the probability, and in here you can write a little phrase, 1 of each. That's okay to write a little phrase in there. So P 1 of each means the probability of you get 1 of each. You can see that there's 1 here and 1 here, which is 2/4 or a 1/2 probability. All right, on to the next page. All right, a family has 3 children, and you want to study the probability of how many boys or girls will be in the family. So list the sample space. Go ahead, take a second, pause it, see what you get. Sample space. Well, the first thing, if we're listing, you got 3 kids, the first thing that could happen is you end up with the Rosema family of boy, boy, boy. No drama in that family, and no weddings to pay for, so that's pretty good. The next thing is the drama-filled, we got girl, girl, girl family. And then after that, we're going to get a mix. So let's have just a little pattern going. First, maybe of a boy first, and then another boy, and then a girl. And then we can have that one female work through the whole. We can have boy, girl, boy, and we can have girl, boy, boy. So that's if there's 1 girl that works through. Now let's do it with 1 boy that works through. We can go girl, girl, boy, and we can go girl, boy, girl, and we can go boy, girl, girl. So those are all the families that can happen, I believe. There should be 8 of them. So we have 8 different things. So that's your sample space. What's the probability that there's only 1 male child? So exactly 1 male child. Well, there's 8 different things that could happen. If we want to find the probability that there's exactly 1 male, we just go through and find the options. It looks like there's 1, 2, 3 of them. So you have a 3/8 probability in your family that you have exactly 1 male with 3 kids. All right, last example. Pause it and give it a try. All right, on Valentine's Day, you want to give your sweetie a box with 12 chocolates. First of all, I would highly recommend not doing that. I would save some money. I think we talked about this a lot with our polar coordinates graphs, and how I would just give her a graph, of a polar coordinate, maybe a rose or a limacon, something like that. Either way, if you have to spend the money, here we go. We have 12 chocolates. There's 4 dark chocolates, 4 milk, and 4 fruit-filled, which sounds disgusting. But if they eat just 1, what's the probability they choose 1 of the milk chocolates? Well, it's pretty clear there's a total of 12 to choose from. 4 of them are going to be milk, so 4 successes out of 12, or a 1/3 probability. Now, choosing 2 is significantly more difficult. We're going to talk about one way to do it now, and then I'll show you an easier way on future videos. But right now, if we're talking about choosing 2, well, on bottom in the numerator, how many ways are there to choose 2? This gets back into combinations. It says that there's 12 chocolates to choose from, and we're going to choose 2 of them. It doesn't say anything about order, so we're going to say, all right, 12 choose 2 is going to be your denominator. If I go on my calculator and do that and go 12, hit math, go over to probability, 12 choose 2, that's 66 different ways. So if I'm choosing 2, there's 66 different ways that you can choose 2 chocolates. Now, if we want to choose, make sure that they're milk chocolates, well, we have 4 to choose from. and we're going to choose 2 of them. So 4 choose 2 is my numerator. So if I'm going to go math, I'm going to go 4, go over to here, choose 2, which is 6. So there's 6 different ways that you can choose 2 chocolates from a group of 4. So this is going to be a 1/11th probability. Now, is there an easier way? Maybe some of you are thinking of it already, and if that's you, very good. We'll talk about an easier way. Have a good day.